Okay, well, welcome everyone, both in person and seeing everyone on Zoom. Your names there makes me so happy. So thank you everyone for coming. It is my great pleasure today to introduce Karoline Eckhart. She comes from Texas and comes to us by way of Cal Poly, where she graduated with a degree in biochemistry in 2017. Since then, she has started work in the Sidlick group. So I have very fond memories of, very early on, Karoline came and actually started over the summer with the group before the school year started. And, I think you told me, I can't start until July 1st. And it was because she had an Alcatraz open water swim that she absolutely crushed, got second. And this just kind of typifies Karoline's personality. She is super tenacious, super determined, super hardworking. It has been my pleasure to be her advisor for the past 5 years. And she has some really awesome science to share with you today. So take it away, Karoline.
Thank you, Stephanie. Thank you for making me start crying right before my presentation. Get this back on my jacket. Again, thank you all for being here today, and thank you all on Zoom for joining us virtually. I'm going to be talking today about my work in developing polypeptide and graphenic-based materials for biomedical applications. Turn my clicker on. So I'm going to start out by giving a brief introduction to biomaterials and defining what a biomaterial is and what they're used for. And then I'm going to talk about 4 projects that have made up the bulk of my thesis work involving the development of peptide and graphenic-based biomaterials. Then I'll close with some overarching conclusions on these projects, and we'll have a Q&A. And if you're listening in on Zoom, please do not unmute yourself during the talk or put yourself on video, otherwise you're going to be captured in the recording. So let's get started talking about biomaterials. When your body experiences an injury, it automatically kicks on a cascade of biological events to automatically repair the injured tissue. And in many cases, like with a paper cut or strained muscle, your body is able to heal itself on its own. But in certain other instances, an injury might be traumatic enough to where your body can't handle it and it can't repair on its own. So you may need a medical device to guide the body towards repair and support healing. There are many different types of medical devices, and their efficacy is all dependent on the type of biomaterial that they're made from. So a wound dressing needs to be flexible in order to move with your skin and also able to maintain an ideal environment for skin healing. On the other hand, an implant or fixation hardware can either replace or support damaged tissue while it heals, and this needs to be either permanent and very strong, like the hardware for a hip replacement, or temporary, like stitches. Another type of medical device is a molecular capture or delivery vehicle. And with this technology, you can either correct a chemical imbalance in the body by capturing a molecular target that's causing the imbalance, or you can release a drug in a specific area of the body to support the healing process. And then a 4th type of medical device is a tissue regeneration scaffold. And with this technology, you harvest cells either from the body or from a donor, and you culture them ex vivo in controlled conditions. And then these cells can be reimplanted into the body to support healing. And like I mentioned before, the efficacy of all of these medical devices depends on the chemical composition and the interfacial properties between the biomaterial from which it's made and the body. Biomaterials can be made from many different types of sources, whether they be synthetic, biological, or biomimetic. So for example, metals like titanium alloys or cobalt alloys are really useful for load-bearing implants because they're very strong. Meanwhile, polyacrylates can either be used as a stiff bone cement or a more flexible and adhesive skin adhesive, just because of a really small chemical difference in their polymer structure. On the biological side, we have 2 major classes of biopolymers, polysaccharides and proteins, or polypeptides, that make up interesting biomaterials. In the polysaccharide side, we have hyaluronic acid and chitosan, which are intrinsically bioactive. And for proteins, we have collagen and elastin. Each of these different biomaterials can either participate in healing actively or passively. So an example of a passive healing technology is like a metal implant or a polyester suture. These are simply supporting the body while it heals. Meanwhile, an active biomaterial is one that's actually changing the chemical environment or interacting with cells in a way that's productive for healing. So an example of this is hyaluronic acid injections in the knees of patients with knee osteoarthritis. Hyaluronic acid is nature's lubricant, and it also plays a role in mediating inflammation. So by injecting this material into the knee, patients not only increase their function, but also have reduced pain because of this change in the chemical environment. So while the CIDLIC group has a role in developing active biomaterials in each of these categories of materials, my work is specifically focused on creating graphite and polypeptide-based biomaterials that can participate in active healing. So in this way, my thesis work contributes to the field of biomaterials development in 3 ways. The first is that I developed a class of polypeptide amphiphiles with a specific application in mind to treat a gap in clinical medicine. The second way is that I report progress towards 2 new ways to synthesize synthetic polypeptides with functions that are related to their sequence of amino acids. And the third way is by creating a series of functional graphenic materials with tunable surface chemistry that have the ability to interact with mammalian and bacterial cells, which are both very important in the healing process. The first 3 projects that I'm going to be talking about involve the synthesis of polypeptide-based biomaterials. So I'm going to give a little bit more background about why we're interested in using polypeptides as biomaterials and how we make them. Like I mentioned before, a protein is a type of natural biopolymer, and it can serve many diverse roles in the body, as diverse as playing a role in structural support, like the collagen that's in your cartilage and your bones, and participating in immune protection, like an antibody. And all of these diverse functions of a protein are because of their hierarchical structure, which is all founded on the primary sequence, which is the sequence of amino acids in the polymer protein chain. And this sequence of amino acids is directly related to these local folding patterns that can either be ordered like a beta sheet or an alpha helix, or disordered like a random coil. And when a protein has multiple domains of secondary structure, it's said to have a tertiary structure. And when proteins with a tertiary structure interact with other protein molecules, they can form a one functional unit, which is called its quaternary structure. Now, researchers are very interested in harnessing some of these functions of natural proteins in a synthetic way by creating synthetic polypeptides. This is essentially a synthetic version of a protein. And by tuning the sequence of amino acids, the primary structure, synthetic polypeptides can adopt secondary, tertiary, and quaternary structures, which have biomimetic functionality. Another advantage to using peptide-based biomaterials is that they're inherently biocompatible and degradable because they're mimicking a natural protein. There are a few different ways that you can make a synthetic polypeptide, but the way that I'm most interested in is through a ring opening polymerization of an N-carboxy anhydride monomer. This is a type of cyclic amino acid monomer called an NCA, and this can be polymerized in the presence of a nucleophile, for example, a primary amine. And in this polymerization, the primary amine attacks the anhydride of the NCA, which causes ring opening. And this molecule decarboxylates, releasing a molecule of CO2 and regenerating this primary amine end group, which can then propagate more monomer. And the result of this is a synthetic polypeptide, where we have control over the molecular weight based on the molar ratio of the monomer to initiator. And we also get low dispersity, meaning homogeneous molecular weight. And this approaches natural proteins. We also are able to access macroscopic sequence control. So we can achieve homopeptides, random, and block copolypeptide sequences. Peptide amphiphiles are a key example of how we can use NCA-ROP to make a functional polypeptide. A peptide amphiphile is essentially a block copolypeptide that features a discrete hydrophilic domain and a discrete hydrophobic domain. And by controlling the amino acid side chain and the molecular weight of the respective blocks, we can access different secondary structures in the peptide amphiphile blocks. And these secondary structures result in tertiary structures and then quaternary structures so that these synthetic polypeptides can form useful biomaterials like vesicles, sheets, and hydrogels, which are interesting vehicles for drug delivery as well as 3D tissue culture and wound dressings. Despite countless advancements in our ability to create functional polypeptides as biomaterials, there's still a few gaps in the field that my research is seeking to address. The first gap is that we need to come up with new applications for these functional polypeptides. How can we reimagine current biomedical materials as polypeptide materials and use the advantages of a polypeptide to address the goals of biomaterials that aren't participating in active healing? The second goal is to leverage NCA-ROP to come up with new ways to create polypeptides with sequence control. And the third gap in the field, which is probably the most important gap, is our inability to create polypeptides with precise sequence control through NCA-ROP. So like I mentioned before, we're able to access homopeptides, random, and block copolypeptide sequences. But what if we wanted to access a truly biomimetic sequence that's more complex than this? Something with either a repeating amino acid sequence or an alternating amino acid sequence. So my work is seeking to address all three of these areas. And the first project I'm going to talk about involves creating a new application for self-assembled polypeptides. And we're specifically interested in creating a technology for gastrointestinal decontamination following a drug overdose. When your body overdoses on a drug, it's hanging out in your gastrointestinal tract and just being absorbed by your body. And if the drug does not have an antidote, sometimes the only treatment option is to decontaminate that gastrointestinal tract. And this is done by administering a slurry of activated charcoal, either orally or through a stomach tube. And the purpose of this is to adsorb the excess drug molecule to the activated charcoal in order to prevent it from being adsorbed by the body. So the drug that I have shown here is amitriptyline. This is a tricyclic antidepressant that is sold under the name Elavil. And this material and many other drugs like it can be adsorbed to activated charcoal through pi-pi stacking, n-pi stacking, and hydrogen bonding. And it helps that activated charcoal has a very high surface area. So it's able to maximize adsorption because it's maximizing the interfacial interactions between the activated charcoal and the drug. But unfortunately, activated charcoal is not a treatment option for everyone. If a patient is unconscious or has an unprotected airway, there's a significant risk of aspiration. And the activated charcoal can accumulate in the lungs. And because activated charcoal is not readily degraded in the body, it persists for a long time and can actually cause chronic lung disease. So we aim to address this problem by designing a class of polypeptide-based adsorbents that serve the same role as activated charcoal in adsorbing drug molecules, but don't carry that risk of persistence in the body because they're a naturally degradable material. So we designed a class of peptide amphiphile adsorbents, which we call keys, and they feature a hydrophilic block made up of lysine and glutamic acid. So the lysine is the K, glutamic acid is the E, and this hydrophilic block affords both dispersibility to the key adsorbent and also it's non-fouling because of the high charge density. The hydrophobic block is made up of polytyrosine, which is represented by Y. And tyrosine features this aromatic side chain, which is both adhesive to aromatic drugs and also cohesive to other key molecules. So it can form discrete aggregates of the key adsorbent, which can adsorb the drug and then sequester it away. And because this material is based on a polypeptide, it's intrinsically degradable and cytocompatible. We made a series of 3 keys, and because we were using NCA-ROP to make these, we have incredible control over the amino acid composition. We also have low dispersity, and we made the keys with 3 different ratios of the hydrophobic block. So key 30 has the highest amount of hydrophobic, and key 10 has the lowest amount of hydrophobic. And we sought to analyze how these materials adsorb different model drug compounds relative to the clinical standard activated charcoal. So to do these experiments, we combined a known concentration of the adsorbent, which is either the key aggregates or the activated charcoal, with a known concentration of the adsorbate. This is the thing that's going to be adsorbed. And we used 2 model compounds to generalize adsorption of different types of drugs. Acid yellow 3 is an anionic dye molecule. It's very easy to quantify because it's yellow. And this kind of generalizes an anionic aromatic drug. Amitriptyline, like I said, is a tricyclic antidepressant. So this is a real drug with a real risk of overdose. And this was chosen to represent cationic aromatic drugs. And after combining these drugs, we incubated them at body temperature. And we performed these experiments in simulated gastric fluid, simulated intestinal fluid, and phosphate buffered saline, which each have different pHs and different salt concentrations that are relevant to in vivo applications. And then we centrifuged the solution to pellet out the adsorbent, which had captured the drug from the supernatant. And then we sampled the supernatant to quantify by UV vis how much drug was left over after the adsorption process. And we conducted a series of these experiments trying to answer 2 questions. The first being, how long does it take for this technology to work? And the second being, how well do the keys adsorb relative to the clinical standard? So to answer that first question, we did a series of kinetic experiments looking at the % of each drug adsorbed over time. And from this data, we can see that the keys adsorb both the cationic and the anionic drugs as quickly as activated charcoal, if not faster. And that equilibrium is reached in about 15 minutes, definitely less than 20, but a little more than 5. We next wanted to quantify the adsorption capacity of these systems. So we measured the adsorbents, the % adsorbed, at different ratios of the adsorbent to the adsorbate. And then we rearranged this data to form a graph looking at the adsorption capacity at equilibrium. So this is the milligrams of drug adsorbed per gram of adsorbent versus the concentration at equilibrium. This is the concentration of drug that didn't get adsorbed after equilibrium was reached. And we fit this experimental data to the Langmuir isotherm model. The equation is shown here. And the goal here is by inputting the QE and the CE values, which we know experimentally, we can back calculate QM and KL. QM is the maximum adsorption capacity of the system. And we can see here that the keys adsorb acid yellow 3 as well, if not better, than activated charcoal, the clinical standard. And they actually adsorb much better than activated charcoal in acidic pH, in the simulated gastric fluid. And this makes sense because in acidic pH, we have our anionic drug and the keys are cationic. So not only are we getting electrostatic attraction between the adsorbent and the adsorbate pair, but we're also getting the pi-pi stacking between the hydrophobic block and the hydrophobic drug molecule. Looking at the data for amitriptyline, we can see that the keys don't adsorb amitriptyline as successfully as activated charcoal, but they do still adsorb some. And this again makes sense because amitriptyline is cationic. So we may be dealing with some electrostatic repulsion between the adsorbent and the adsorbate, but we're still able to get some adsorption because of the pi-pi stacking. We next sought to understand why these results were happening. So we look at the KL value for this. The KL value is the Langmuir constant, and this can be related to the surface area of the adsorbent and the porosity, implying that a higher surface area and higher porosity results in a higher KL value, which enables higher QM value or higher maximal loading. And we see here that the KL values for activated charcoal are 2 to 3 orders of magnitude larger than the keys. And this result suggests that activated charcoal has a much higher surface area compared to the keys, and that's what's really driving its successful adsorption. Both of these results lend themselves to some future directions in the project so that we can design more effective keys that are specifically designed to adsorb certain drugs. So our result, looking at how the keys are best at adsorbing negatively charged drug molecules as opposed to positively charged, leads us to the future direction of designing the hydrophilic block of the key to selectively adsorb different types of drugs. So if we can choose amino acid side chains with different pKa's to create a cationic or anionic or even neutral hydrophilic block, we can selectively adsorb drugs that are of the opposite charge. A second future direction for this project is increasing the surface area of the keys. So we found that through the KL values, the low surface area of the keys is really what's limiting their adsorption. So if we could design a system that's more three-dimensional, such as a star polypeptide, we might be able to access some intermolecular aggregation of the hydrophobic domains that create these nanoporous pockets that could be used for drug adsorption. The next project I want to talk about today deals with my goal of leveraging NCA-ROP to create polypeptides with sequence-driven functionality. So typically when you're making a peptide amphiphile or block copolypeptide, and this is actually the way that I made the keys, we use sequential monomer addition. And with this strategy, you first polymerize an NCA with a certain amino acid side chain, and you form the polypeptide. And then you add in a second type of NCA with a different amino acid side chain, and this gives you a block copolypeptide. And this is commonly used to make any kind of block copolymer or block copolypeptide. But we wanted to create a way to make this block copolypeptide synthesis more convenient. What if we could just add in all the monomers at once, set it and forget it, and come back the next day and have a peptide amphiphile? We wouldn't have to worry about catching this propagation right at the end and then adding in our second monomer at the precisely correct time. So we rationalized that we could create a copolypeptide polymerization system that is reliant on different reactivity of the monomers. So we proposed creating a one-shot synthesis by combining an N-carboxyanhydride with an N-thiocarboxyanhydride monomer, each with a different amino acid side chain. An N-thiocarboxyanhydride is like the cousin of an NCA. It has a sulfur as the pendant atom in the anhydride rather than an oxygen. And this makes it less electrophilic and have higher stability and lower reactivity. So we theorized that by combining these two monomers in one shot, we would get selective propagation of the NCA at the beginning of the reaction. And then once the NCA was consumed, we would get propagation of the NTA. And I want to note here that NCA and NTA monomers propagate by the exact same mechanism, and they result in identical polypeptide products. So by combining these materials, we aren't actually seeing a difference in the backbone of the polypeptide that we're making. And we theorized that we could use this one-shot copolymerization to make peptide amphiphiles with interesting architectures. So we wanted to use this one-shot synthesis to create a functional peptide amphiphile. So we selected lysine as the hydrophilic block on the NCA and leucine as the hydrophobic block on the NTA. And we polymerized these and studied the copolymerization kinetics to identify if it was actually forming a block. And what we can see here is that in the beginning of the polymerization, we get rapid consumption of the NCA monomer, adding on that hydrophilic block. We are still getting some consumption of the NTA during that first phase. And then when the NCA is fully consumed, we get polymerization and propagation of the NTA. to form a gradient copolypeptide. As another measure to evaluate the blockiness of the peptides, we looked at the reactivity ratios. So by comparing the copolymer composition versus the comonomer feed ratio, we could fit that experimental data to the Milo-Lewis equation and give reactivity ratios. This means the rate constant of the ratio of the rate constant of homopropagation to cross propagation. And what we found here is that the NCA monomer has a reactivity ratio much greater than 1. And this means that when both monomers are in the solution, we get preferential propagation of the NCA over the NTA. And that the reactivity ratio of the NTA is less than 1, which means that even if an NTA just added to the polymer chain, it prefers adding another NCA on top of that. So with these one-shot peptide amphiphiles in hand, we wanted to evaluate if they were still capable of assembling in aqueous solutions, similar to how a normal block copolypeptide would be able to assemble. So we looked at assemblies of various one-shot peptide amphiphiles with different comonomer ratios and monomer to initiator ratios. And we found that the type of assembly of these one-shot peptide amphiphiles really depends on the length of the discrete polyleucine block at the end of the polymer, that hydrophobic block. And we found that when the DP, or degree of polymerization, of the polyleucine block was low, between 5 and 12, we either got irregular aggregates or very small micelle type structures. And then when we increase the length of that discrete polyleucine block, we either get stiff sheets or more spherical vesicle type structures. So overall, this work contributes by coming up with a more convenient way to access a functional copolypeptide amphiphile by using a one-shot polymerization. And this could be a more accessible technique for interdisciplinary labs that might not have ready access to an NMR or an FTIR, where they can actually check conversion of that first block to make sure that it's been completed. The next project I'm going to talk about involves achieving more precise sequence control using NCA-ROP. So as I mentioned before, we can make block copolypeptides, random and homopeptides using NCA-ROP. But there are certain interesting biological proteins like collagen that exhibit repeating amino acid sequences. So collagen, for example, has a glycine proline proline sequence or glycine X proline sequence. And this material could be really useful biomaterial for replacing cartilage or making a bone composite, something like that. But currently we have no way to access this type of sequence control using a controlled ring opening polymerization. So we sought to address that by developing the first ever NCA-ROP to make sequence polypeptides that are identical to a natural polypeptide using a macrocyclic NCA polymerization. So with this approach, we start with a sequenced oligopeptide, and then we cyclize that to form a macrocyclic NCA that's encoded with the amino acid sequence of the oligopeptide. And then we could polymerize that using a controlled ring opening polymerization to give a synthetic polypeptide with a repeating amino acid sequence. And because this is NCA-ROP, we expect this to be scalable and atom efficient, and critically would allow us to access repeating and alternating copolypeptide sequences through controlled polymerization for the first time. So our first target for this project was a collagen mimetic protein. For the reasons I stated above, this could be an interesting biomimetic material as an implant. So we started out by creating the glycine proline proline amino acid trimer through a 4-step synthesis. And our overall yield here was about 24%. And I want to point out here that the yields of each of these reactions was pretty high, except for this one here. So that's a future direction that we're working on. But with the amino acid oligomer in hand, we cyclized it to form this GPP-NCA macrocycle, which we were able to confirm the successful synthesis of this using high resolution mass spec, where we saw the exact mass adducts representing the GPP-NCA. But unfortunately, this material is extremely unstable, and we can actually witness its instability in real time. In looking at an FTIR of GPP-NCA, we're zoomed in here on the carbonyl region. We can see the presence of anhydride peaks, which represent the anhydride in the macrocycle. And then after sitting on the FTIR crystal for just 5 minutes, we see a reduction in the size of these anhydride peaks and the appearance of a CO2 peak, which corresponds to degradation of the NCA and release of the CO2 from the anhydride. And then after 10 minutes on the crystal, we have no more anhydrides and we're not releasing CO2 anymore. So this really told us that GPP-NCA, while it might be an accessible target, is too unstable for us to purify right now. So we wanted to switch our focus to GPP-NTA, which, as I mentioned before, is more stable, less reactive analog to an NCA. But in order to create an NTA, we first have to tag on this ethyl thiocarbamate group on the N-terminus, which adds a step to the synthesis and also reduces our overall yield to about 18%. Nevertheless, we took this material, we cyclized it to form the GPP-NTA, again, confirmed that synthesis using high-resolution mass spec. And we also were able to use FTIR to suggest the successful synthesis of GPP-NTA. We can see here that GPP-NTA has the appearance of a thioanhydride peak, representing this part of the molecule. And it also sees a shift to a higher wave number of the amine peak right here. And these differences are not seen in the linear starting material. The changes are, however, consistent with a simulated FTIR spectra of GPP-NTA that was prepared by Chris Kotke and Professor Marina Kurnikova in collaboration. But there were still some challenges with this synthesis, mainly that there was low conversion from the linear starting material to the macrocyclic NTA, and that it was very difficult to purify, and we were actually not able to purify GPP-NTA successfully. Nevertheless, we went forward with a proof of concept polymerization in the presence of the impurities just to see if this molecule would actually ring open to form a collagen mimetic polymer. So we treated the GPP-NTA with a primary amine and polymerized it, and then analyzed the product by size exclusion chromatography and NMR. And we can see here that the SEC has a multimodal peak distribution, which suggests multiple polymer species present in the sample. Typically in a controlled polymerization, you just have one peak in the SEC and it's very narrow. So we can see here that we clearly do not have control over this polymerization, and it's probably because the presence of those impurities. We also analyzed the polymer by NMR, and we determined that the average degree of polymerization was about 7, which really means 21 amino acid units in a row, because each monomer is 3 amino acids. And while we're still working towards creating this collagen mimetic macrocycle and polymerizing it, we wanted to shift our attention to a more synthetically accessible macrocycle. So we chose KD-NCA right here. And the advantage of KD-NCA is that it's only a 2 amino acid sequence. And that means that it takes less steps to make the starting material. It only forms an 8-membered ring, which generally has less ring strain than an 11-membered ring that's bicyclic. And we specifically chose KD as our amino acids because this material would be a zwitterionic copolypeptide, which could be a useful replacement for PEG, or could be used to make a non-fouling surface. So we prepared our KD dimer, and this was a 2-step synthesis with an overall yield of 89%. We love that. And we could make it on a multi-gram scale. So this enabled us to get many tries in optimizing the synthesis of KD-NCA. We were able to prepare KD-NCA and confirm its synthesis by high-resolution mass spec and heteronuclear multiple bond correlation. And with the HMBC, this is pretty cool. We're zoomed in on the protons on carbon K, the proton NMR, and this is carbon K. So we're looking at this proton, and HMBC is showing us correlations to carbons that are 2 to 3 bonds away. And we can see here that the proton on carbon K is correlated to 4 carbons, which can be identified as these 4 carbons here. So this data is confirming ring closure because in the starting material, the proton on carbon K is only correlated to 3 carbons. But when we close that ring by this anhydride, we get an extra correlation. Unfortunately, there were still some complications with this. The main one was that we were getting some side reactions in this reaction that probably led to, or were the reason behind poor conversion. We only reached about 60% conversion after 5 hours, and that was plateaued. And because of these side reactions and the poor conversion, the purification strategy was very difficult. We were able to purify this, but the yield was only about 12%, which I see as kind of a loss, but Stephanie always reminds me that 12% yield for a macrocyclic peptide is actually really good. So I want to be better though. So that's a future direction. So like the last project, there are a couple challenges in this project that we seek to address in the future directions. For one, we weren't able to reach high conversion with either the NCA or the NTA synthesis. So our way to address that is by adding in a scavenger to push the equilibrium towards product formation. So for example, in the NCA synthesis, one of our byproducts is HCl. So if we can add in a scavenger that removes that HCl, we may be able to push the equilibrium towards ring closure. The other challenge we found was that the purification was a challenge. And we seek to address that by investigating some polymerization strategies that are impurity tolerant. So some recent work has come out of the Chain group to develop impurity tolerant polymerization. They can polymerize crude NCAs extremely rapidly by using a technique that they call simple. And because the rate of propagation is so fast, the rate of any terminating or side reactions that could go down with the impurities is essentially negligible. So we'll be looking into this too, but it kind of requires us to be able to reach high conversion and limit the amount of impurities. They can still be present, but they shouldn't be dominant. The last project that I'm going to talk about involves my work with creating functional graphenic materials with tunable surface charge as a way to control bacterial and mammalian cell fate. But to understand why we're interested in this topic and why these materials might be useful as a tissue scaffold or as an implant material or wound dressing, it's important for us to understand some of the key criteria for a cell scaffold. A cell scaffold should have controlled surface chemistry. This means we can tune the hydrophilicity or the charge of the surface in order to promote cell adhesion, proliferation, and differentiation. We also want a biomaterial to be bioactive. We can tag on some signaling molecules to communicate with the body and accelerate regeneration. Electrically conductive materials have been shown to enhance adhesion and proliferation of cells. And they can also be used in electrotherapy, where you're stimulating cells with electrical conductivity through the scaffold in order to promote a cellular response. Mechanical match is also an important feature. You want the mechanical properties of the scaffold to match those of the cells that you're trying to regenerate. And if it's too stiff or too soft, it's not going to be as successful of a regeneration. And you also want your material to be biodegradable, especially if it's going in the body, so that we can avoid any unwanted persistence in the body. And finally, biocompatibility is crucial so that you're not having some kind of cytotoxic effect or eliciting a counterproductive immune response. Graphene can be a really useful platform for the creation of biomaterials for cell scaffolds because it can be tuned to fulfill these criteria. Graphene is a two-dimensional nanocarbon material made up of sp2 hybridized carbons, and it's intrinsically conductive and mechanically strong. So it's already checking some boxes for an ideal cell scaffold. Graphene can be oxidized to graphene oxide through my favorite route, the Hummer's method. And this installs a series of hydrophilic functional groups on the basal plane and the sheet edges. And these functional groups can serve as chemical handles for further functionalization if you want to tag on any kind of signaling molecule or polymer that you want. but oxidation of graphene to form graphene oxide comes at the expense of some of the mechanical strength and conductivity. So you can reduce your graphene oxide down to RGO, either using heat, UV radiation, chemical reduction, and you can create this reduced graphene oxide material that has kind of the best of both worlds. You've got the chemical handles on the surface and edges, as well as the mechanical properties and the conductivity. My work is specifically focused on tuning the surface chemistry of the graphenic materials in order to promote active healing pathways and to have productive interactions with mammalian and bacterial cells. And then also investigating how changing the surface chemistry of a functional graphenic material, or FGM, changes the mechanical properties, the conductivity, and the other properties of the material. So before I came to CMU, the SIDLIC group was already working on a pathway to create functional graphenic materials with tunable surface chemistry. And the approach they were using was grafting a peptide from the surface of the graphenic material. So they started out with a reduced graphene oxide that has these nucleophilic alcohols. And then they treated it with an N-carboxy anhydride monomer to polymerize a peptide from the surface. And this resulted in a powder material that was cytocompatible and where the identity of the functional groups on the surface could be tuned by the identity of the amino acid side chain of the NCA. And these powder materials could be pressed into a 3D pellet that were mechanically strong. But this synthesis had some drawbacks. For one thing, there was a relatively high input of NCA with a low output of material. And another issue with this is that the peptides were fairly short and there was no control over the molecular weight of the peptides. Because graphene oxide is a heterogeneous material, you don't actually know how many moles of initiating groups that you're adding with respect to the monomer. So you don't have control over how long the peptides are or how many peptides there are. So my goal was to optimize the synthesis of PepG so that we can create more material, higher yields, more reproducible, and start to investigate the real cellular interactions between this unique PepG material and mammalian cells and bacterial cells. So we switched to a grafting 2 approach. And this is where we polymerize the NCA in a separate flask, initiated with a known amount of primary amine initiator to create our polypeptide with this active amine end group. And then in a separate flask, we convert graphene oxide to Claisen graphene, which is essentially installing carboxylic acids on the basal plane to replace some of these primary alcohols on graphene oxide. And then we can activate the carboxylic acids to form acid chlorides and use this electrophilic Claisen graphene to quench the amine end group of the peptide to form this covalent PepG conjugate. And the result of this switch in the chemical synthesis was that we were able to create PepGs where the molecular weight of the peptide was controlled and that the dispersity was low. And we also were able to yield 9 times more PepG material than the original procedure. And we made a bunch of different types of PepGs with lysine and glutamic acid. We made block copolypeptide PepGs and random. But the one that I'm going to be talking about today is PLLG, which is poly-L-lysine G. And this has an amino acid side chain with a cationic amine. And we wanted to compare this to the anionic parent materials, Claisen graphene and graphene oxide, to answer a few questions. We wanted to confirm that the chemical functionalization allowed us to control the functional group, the amount of functional groups and the types of functional groups on the surface. And we wanted to evaluate how the peptide graphenic conjugation route impacts the mechanical properties and the conductivity of the material. And we also wanted to investigate the interactions of these materials with different cell types. So to answer that first question, identifying the types of functional groups and the amounts of functional groups on the surface, we use X-ray photoelectron spectroscopy. And this is a technique where we can not only get information about the composition of atoms on a surface, but we can also identify the types of functional groups that those atoms were participating in on the surface. So for graphene oxide and Claisen graphene, We are interested in looking at the carboxylic acids, which are contributing the negative charge. So we're looking at high resolution carbon XPS down here, which shows a multimodal peak distribution where each subpeak is a different carbon containing functional group. And we can see here that the graphene oxide has about 2.2% of all atoms on the surface are carbons participating in a carboxylic acid. And then when we transform this material to clays and graphene, we see an increase in that number to about 3.5%. And this chemical change is manifested in an increase in the magnitude of negative charge on clays and graphene relative to graphene oxide. And then with the PLLG, we made two different types. We made one with a degree of polymerization of 6 and one with a DP of 50 on the peptide. And we're looking at the high resolution N1S, or the nitrogen here, to identify the presence of ammonium and amine peaks that represent the source of the cationic charge on this material. And we can see that the zeta potential of the PLLGs are both positively charged, and that the magnitude of that positive charge depends on the degree of polymerization of the polylysine, either 6 or 50. And so overall, we established this synthetic pathway that gave us access to a series of FGMs with different controllable surface chemistry and resulting differences in the surface charge. And we wanted to evaluate how that impacts the material properties. So we pressed the powder materials into 3-dimensional pellets, and we tested the ultimate compressive strength to represent the mechanical properties and the conductivity. And we can see here that transforming GO to clays and graphene results in a stronger material, and that conjugating a peptide to the clays and graphene does not sacrifice the mechanical strength. And then with the conductivity, we see an increase by 2 orders of magnitude in transforming GO to CG. And then we see a further increase of 2 orders of magnitude in converting clays and graphene to a PepG. And we sought to understand why this happens. This is actually kind of an interesting phenomena because a peptide is not mechanically strong and not conductive compared to a graphenic material. So why is it that adding a peptide into the equation is actually retaining the mechanical properties and enhancing the conductivity? And we can actually chalk this up to 2 theories. The first is that the covalent linkage between the peptide and the graphenic components of these conjugates is preventing phase separation. So to confirm this, we made a few controls by blending clays and graphene with a peptide together to make a non-covalent PepG. And this material had, I want to get this right, it had 100 times smaller ultimate compressive strength and was 3,000 times less conductive than the covalent PepG. So this really shows us that the covalent linkage between the graphenic and the peptide component is crucial to access these good mechanical and electrical properties. And the second reasoning behind this result is likely due to the level of reduction. So over here on the right, we're looking at the Raman spectroscopy of each of the FGMs. And Raman is a technique that researchers commonly use to evaluate the level of reduction of a graphenic material by comparing the D band to the G band and their intensities. So here, a higher intensity of the D to G band indicates a more reduced material, and a more reduced material is generally more conductive and more mechanically strong. And we can see that the trends seen in the intensity of the D to G band correlate to those in the ultimate compressive strength and the conductivity, suggesting that the level of reduction of these FGMs is a really important feature in enabling them to have good material properties for a regenerative scaffold application. Ooh, too far. So with these properties in mind, we wanted to evaluate how these FGMs could be leveraged in a cell regeneration scaffold. So in this experiment, we were working with PC12 cells, which are a neural progenitor cell type. It's basically like a baby nerve cell. It hasn't been fully matured, but it has a propensity to differentiate into a nerve cell under the right conditions. And we cultured a pellet of the PLLG and the clays and graphene, which is our cationic and anionic FGMs respectively, with the PC12 cells, and we applied electrical stimulation to the pellet in order to drive differentiation of the cells. And after 2 days of electrical stimulation, we found that there were numerous cells on the surface of the PLLG pellet and that they started to have some of these neurite-like outgrowths, indicating successful beginnings of differentiation. And then with the Claisen graphene, on the other hand, we had far fewer cells and they remained in this undifferentiated, immature state. So this result signifies the utility of PLLG for use as a scaffold for electrotherapy. We next wanted to evaluate how these FGMs interact with bacterial cells. Understandably, the GO and the Claisen graphene were well tolerated by both gram-negative and gram-positive bacteria. This has been reported widely in the literature. And so this was an expected result. But shockingly, the PLLG was actually also compatible with bacteria. It did not cause a decrease, a significant decrease in the culture density of the bacteria. And this was surprising because PLL on its own, just the free polypeptide, is toxic to bacterial cells. We can see a large reduction in culture density when treated with the PLL control material. So with this result, we hypothesized that the PLLG, because it has a peptide that's immobilized on the surface, the peptide isn't able to insert itself into the cell walls of the bacteria as readily and cause cell death. And so now we're looking at some materials with tunable surface charge. They're not toxic to bacteria. How can we investigate these materials as a way to control bacterial adhesion without sacrificing the vitality? So because bacterial cell walls are made up of, they have these polymer chains sticking out through the cell wall that are anionic, we expected that the different charge of the FGM would be able to control bacterial adhesion through electrostatic interactions. And we tested this by culturing pellets of our negatively charged Claisen graphene with our positively charged PLLGs, and then staining the bacteria with a dual dye stain where living cells are stained green and dying cells are red. And we can see that the Claisen graphene has very few bacterial cells on it. It doesn't have very much green or red at all. So this one is considered bacterial repulsive because the negatively charged material is repelling the negatively charged bacteria. And then with the PLLG, we see numerous bacterial cells on the surface of the pellet, and they're mostly living, which is consistent with our hypothesis that a positively charged material would adhere negatively charged bacteria. And this result was confirmed using scanning electron microscopy. We can see the bacteria cell walls appear to be intact. They appear to be happy living on that surface. This work caught the attention of some collaborators at the Federal University of the San Francisco Valley, and they were interested in leveraging the FGMs to create a xenograft based on tilapia skin. So tilapia skin is an inexpensive and abundant resource that is high in collagen content. So it's really useful for supporting skin healing in a wound dressing application. And it also has good mechanical compatibility with skin. And this is why it's been used clinically in Brazil to address the wounds of burn patients. But unfortunately, this material carries a risk of bacterial contamination and also biofilm formation. A biofilm is very bad. This means bacteria are stuck to the surface, they're proliferating on that surface, and they're laying down a extracellular matrix of proteins and other junk that is making them resistant to antibiotics. So if you have a biofilm, you basically have to remove the implant and try to just decontaminate as much as possible. So our approach was to modify tilapia skin with these FGMs to impart bacterioinstructive properties. Can we control bacterial adhesion on the xenograft using the FGM? And we found that tilapia skin, as expected, has a large amount of biofilm, which was quantified by crystal violet stain, and that all of the FGMs, regardless of their surface charge, actually reduced the biofilm formation on the xenograft models. But that the most negative FGM, Claisen graphene, was the most successful at reducing biofilm formation on the tilapia skin. It resulted in an 88.8% reduction in biofilm relative to tilapia skin on its own. So overall, This result told us that the negative FGMs could be a really useful application in wound dressings as a way to repel bacteria without having to use an antibiotic and have that risk of potential antibiotic resistance. So conclusions with this FGM work. We developed a class of functional graphenic materials where we could tune the surface charge of the material by adding on different chemical functional groups on the surface. And we established the bulk properties of these FGMs, which demonstrate utility in an electrotherapy treatment for nerve regeneration. We next demonstrated the bacterioinstructive activity of the bulk FGMs and applied the FGMs in a xenograft model where Claisen graphene, the most negative, was found to inhibit biofilm formation the best. Some future directions for these FGMs include improving the synthesis of the PepG so that it's more green. So while in theory, the NCA polymerization is green because it's very atom efficient, it does still use some pretty nasty solvents that are bad for the environment and could potentially limit its scale up. So work in our group, specifically by Michelle Wolf, has been dealing with improving the PepG synthesis even further to use more environmentally friendly solvents and more gentle reaction conditions. And another future direction in our group is to fabricate the FGMs and other PepGs into three-dimensional scaffolds. So the scaffolds we looked at today are bulk, meaning that the powder is just pressed into a pellet. But unfortunately, these materials, these pellets, are not very porous. And because their activity relies on interfacial interactions, this is pretty wasteful of the material. So we want to figure out a way to leverage the FGMs as a coating so that we can maximize their interfacial interactions, or perhaps load them into a composite to be more material efficient. And current work in the group is also investigating 3D printing the FGMs so that we can create scaffolds for both in vivo implants and in vitro cell regeneration. So I want to highlight some main takeaways for the work that I've talked about today. One of them is that surface and interfacial properties of a biomaterial are really the key to dictating how it's going to interact with the environment, whether that be other cells or other molecules. The second takeaway is that structure-function relationships are key. If we can leverage organic chemistry to change the chemical structure of a surface or of a biomaterial, we can control both the macroscopic and the molecular interactions of biomaterials with the body so that we can create biomaterials that can participate in active healing. And with that, I would like to thank my thesis committee, Stephanie, Doss, Kevin, and Dan. Thank you all so much for your time contributing to this work. I would like to thank my collaborators at the Federal University of the San Francisco Valley who conducted the studies with the tilapia skin, as well as my funding. I'm already gonna cry. I wanna thank Stephanie for being the best advisor and just always supporting me and making me feel confident in my work and just being amazing. Thank you, Stephanie. I also want to give a special shout out to my undergrads who have played a massive role in the work that I've talked about today. Training these undergrads has been one of the most fulfilling things in my grad school experience. Thank you, Tarek. Thank you, Anna. Thank you, Callie and Sasha, Francesca, all of you on Zoom. Thank you so much for the work that you've done on these projects. And I also want to thank my group for being so supportive of me. You guys are incredible, and I would not trade any of you for anything. Thank you so much for how much you've supported me over these past years. And I want to thank my family and friends, especially Justin, for holding it together for me these past 5 years, and especially the past 3 months while I've been writing my thesis and preparing this talk. I would literally be eating ice cream every night for dinner if it weren't for Justin, so thank you. And I want to thank my friends, Mike, especially, and Seth and Megan. for supporting me through this whole time and just being a person I can vent to and just helping me with any question that I have and any problem in research. I also want to thank my undergrad advisor, Phil. He's kind of the reason why I came to CMU. He went to CMU and inspired me to come here. No regrets. I have loved working at CMU, loved working for Stephanie. I also want to thank my family for their support and Roberto for teaching me how to leverage NMR for my research. Oh, here's a mechanism. Thank you so much. I will happily take questions now. Thank you. I should have brought tissues. Here, get down.
All right. So thank you. We'll take questions now for the open part of the defense. For this lovely hybrid format, I'm going to actually take any questions that we might have from Zoom first. So if you have a question on Zoom, feel free to type it in the chat or just unmute yourself, turn on your video and ask it. Don't have to turn on your video, but that'd be nice.
I have to let the Zoom participants unmute themselves.
There we go.
Okay.
Well, I don't see anything on Zoom. So while I'm waiting for anyone there, do we have any questions in the in-person audience?
Yeah.
When you were key multi-block, why did you choose blocks of the hydrophilic and then one block?
Yeah, that was actually, the hydrophilic is a random copolypeptide. So we just added in 50-50 ratio of the lysine to the glutamic acid. And the goal there was to create a Zwitter-ionic hydrophilic block so that it could change the charge of the key based on the pH that it was in, so that we could get some different electrostatic interactions with different molecules. And we also wanted it to be Zwitter-ionic for the non-fouling aspect. So recent research has shown that Zwitter-ionic polypeptides actually mimic natural proteins by exhibiting that high charge density on the surface of the peptide. And this prevents cytokines from coming in and trying to eliminate the peptide prematurely, basically like slows down the degradation.
Good question.
Stephen?
Can you go to slide 11?
Mm-hmm.
Yes, so activated charcoal is mainly carbon.
Yes.
So how does something made with carbon and hydrogen dissipate hydrogen?
Well, it doesn't just have carbon and hydrogen. It's mainly carbon and hydrogen, but we've actually done XPS of this material and have seen the presence of functional groups like ketones. And I think the presence of those functional groups has to do with the source of the activated charcoal. Like, what did it start as? It can be made from bamboo. It can be made from various types of like polysaccharides and other like natural materials. So in the process of exfoliating that to activated charcoal, you can still have some remaining oxygen containing groups that can participate in that.
So I guess related to this project, you said there was a difference in surface area between your composites and the active charcoal. Do you have like an estimate of how much that difference was?
Yeah, so we actually tried using BET to evaluate the surface area of the keys versus activated charcoal so we could actually quantify that difference. And I have the data. Need to look at my supplemental slides. It's in one of these. Here we go. Slide 78. All right, so we can see that with activated charcoal, this is what it's supposed to look like. We have increased amount of adsorbed gases relative with the relative increase of relative pressure in the chamber. And this can be used to quantify the surface area, which was about 693 meters squared per gram for activated charcoal. And when we tried the same analysis with Key 20, we got a terrible BET fit. And we think this is because the keys have such a low surface area that it's actually below the limit of detection for the BET. And we would probably need to use like 10 times more material in order to get a valid surface area measurement. But I still think this data kind of communicates that the keys are much, much less surface area than activated charcoal, just because using the same amount of material, we were well above the sensitivity of the instrument with activated charcoal and not even close with the keys. Megan?
Is there anything you could do further preventing biofilm accumulation?
Yeah, definitely. So I think something that is engineered to be released from the graphene surface, for example, like gentamicin. Gentamicin is an antibiotic with amine groups on it. So we could use that to covalently link it to the graphene. And if we could get that material to be released from the graphene surface or hydrolyzed, then it can actually exhibit toxic effect to the graphene. But I think having the antibiotic in such close contact to the graphenic surface creates kind of a steric block between the bacteria and the antibiotic, which basically suppresses its activity. Michelle?
Given that your key polypeptide materials are peptides and therefore degradable, do you think they will stay intact in the body long enough to hang on to the drug and be full?
Yeah, that's a great question. So in the design of the keys, by having that zwitterionic hydrophilic block, our intention is to increase the lifetime of the key in the body. But we would need to do some studies on that to actually confirm if we're getting increased lifetime and how long that lifetime is. So we'd probably start with some in vitro studies looking at taking the peptide with the encapsulated drug, treating it with an enzyme that degrades the peptide, and see how long it takes to re-release that drug. And if it's much slower than a standard activated charcoal or another type of polypeptide-based adsorbent, then that would be a success. Key?
Just to follow up on that question. So for slide 14, we talked about the keys. So is it quantitative? So after a key absorbs, it absorbs only 14.
Oops.
After it absorbs all the like drug molecules, and if there's any leftovers, to always aggregate by themselves or just like float around.
So the keys are actually already aggregates in the system. So we're adding them like as a dispersion to a drug solution. And we assume that the keys all have equal ability to adsorb drug because of the relationship between increasing the amount of key results in more drug adsorbed. So in the process of centrifuging them to pellet out the key with the sequestered drug, we don't expect to see any key left over in the solution. And we actually tested that using UV vis by taking a control of just the keys with no drug and then centrifuging that and testing the supernatant. We didn't see any leftover drug just hanging around in that supernatant. Thank you. Hunter?
Yeah, regarding your future work with the keys, I think you had a graphic relating to like a gel based or like a structural polymer.
Oh yeah.
Yeah. So would you theorize that having more arms on that or less arms would lead to?
That's a great question. I want to go back to the slide that he's talking about. So he's talking about this proposed, too far, dang it. Okay, this proposed assembly of this 3-arm star polymer, which has the pockets here. And I actually think that more arms on this, depending on how I think more arms on this would just create massive aggregates and maybe wouldn't adsorb as well because the drug might not be able to like penetrate through those big particle sizes. But if we were to flip the hydrophobic as the core and the hydrophilic as the exterior and add more arms, we would be able to create unimolecular micelles, which could be a cool drug adsorbent target on its own because it's basically, it doesn't rely on intermolecular interactions to form a functional unit. It's very small. So possibly would have higher surface area. Yeah, so that's a future direction too. You should check that out, Hunter. Yeah.
I have a question from slide 50. Yeah, so regarding this option formula, you said that you have values of QE and CE, and then we can back calculate values of QM and KL.
Yeah.
So we have just one equation and we have two unknown variables.
How do we do that? I use Solver in Excel, and that's basically where I have my experimental data. And then I create fake or calculated values of QE based on my known values of CE, where I'm inputting just a guess on what QM and KL are. And then using the Solver plugin in Excel, Solver automatically changes the QM and KL values to decrease the difference between my experimental QEs and my calculated QEs. So this allows us to do a nonlinear fit for this experimental data. Mhm. One more, Kai?
On slide 9, we talked about with the walkable with higher filling. How exactly are you going to feel like? Is it easy to sort of possibly create listics or like is it that?
Yeah, so these are actually made using that sequential monomer addition strategy, where you first polymerize the hydrophilic amino acid block, and then you add in the hydrophobic NCA, and then the hydrophobic just polymerizes right off the end of the hydrophilic block. Without any, well, I mean, ideally, you don't have any termination going on when this is polymerizing. If you do have termination, then you would have inefficient grafting from the end of the hydrophilic chain ends. Let me check the chat, see if anyone has. Yay.
Lots of nice messages. So maybe you want to.
Thank you, Zoom people.
Yeah, thank you everyone on Zoom for attending. It was great to see you. I will say we will open the Zoom room back up when we go upstairs. Hope, fingers crossed, yeah. So we'll let you know when that is. But I think if there are no more questions here in person or on Zoom, this will conclude the public part of the examination, and we'll move into the private. So great job, Caroline.